Hello, everybody. So, this podcast is a summary of some of the tough topics that will be on your test. And before I do the three problems that I want to go over, I wanted to show you a summary of everything that we've learned. So, solubility curves, make sure you understand how to read them. Make sure you know whether something's super saturated, it's above the curve. If something's saturated, it's on the curve. And if something's unsaturated, it's below the curve. And you also have to understand that the higher the temperature, the more the solids will dissolve, and it, it, it is the opposite for gases, right? And um, for gases, if you increase the pressure, it actually increases the solubility. So that is one way you could increase solubility in gases. And in terms of solubility curves, make sure that if you're given um, a certain temperature and it asks for how many grams of that solute will dissolve in a certain amount of water that is not 100 grams, then you have to make an adjustment using ratios. So if it does give you 100 grams of water, you don't have to do that because you could just use the graph right away. But if you're not given 100 grams, then you have to make that adjustment and then use the graph. These are the concentration formulas. Molarity is typically used when we're finding the concentration of something that's diluted. Know when to add, know when to subtract. So usually when it's asking for the volume of water that was added to a solution, you usually have to subtract at the very end. So you subtract in order to figure out how much water was added in the first place. And sometimes you don't have to add volumes. If you're trying to find the final molarity, you don't have to add volume if it tells you that it's going to go up by a certain amount. But if it says, oh, I am going to add a certain amount of water, then you have to add the volumes in order to plug in for V2. If that doesn't make much sense, then you want to do the problems and take a look at that. Molality is special. It's another form of concentration, and we typically use that to find the temperature change when something is boiling or something is freezing under a solution. So make sure you understand those items. Here's question 10. It says a solution. So again, if you have a solution, the temperature that something boils will go up. It will go up. And if it's a solution, again, the freezing point will drop. So this is a problem that involves boiling. So the first thing we do is write our formula. So our formula, molar mass of the solute. So that means molar mass is equal to grams per mole. Do we know the mass of the solute? Yes, we do. It says that it is 8.50 grams. Right, it's right here. 50 grams of compound is placed in that much water. However, we don't know the mole. That's what we have to figure out. Now, because it's a boiling point problem, we are going to use this equation, delta T B equals KB times M. Okay, so there's that. And because we're trying to find the mole, it's hidden in here. Okay, it's in there. So we're going to solve for that. And when you solve for that, you get delta TB over KB. Then you have to figure out the temperature change. It's not given to us explicitly. It is actually something you have to figure out because it says that the solution boils at 100.78. So if the solution boils at 100.78, so that's your solution, and you subtract that from the boiling point of water, of just pure water, then that will give you the change in temperature, which is 0.78. So we could plug that in, 0.78 And our Kb value is going to be on your chart, so you have to look for it. 0.512 degrees Celsius per molality. And when you cancel, you get your molality, which is 1.523 moles, or little m, which is the same as moles per kilogram. Okay, so sometimes, you get a little lost and you're like, okay, I lost track of what I want. I don't want molality, I want the molar mass of the solute. So again, we have the grams of the solute. We need the moles. And according to this molality, we have moles of solute right here. The problem is that we have the kilogram in the bottom, so we need to get rid of that. And the only way to get rid of that is by multiplying by the kilogram of your solvent, because molality is defined as moles of solute over kilograms of solvent. So we need to multiply by the mass of the solvent, which in this case is 22.6. And if you divide by 1,000, you get this. And so your mole will be 0.0344 moles. And so if it was asking for moles, you would stop there. If it's asking for grams, you would use the molar mass of this compound, but that's not what we want. And 2, we don't know what that compound is. And so all we have to do now is plug that in here, and we have our molar mass, which is what we want. And our molar mass will end up being 247 grams per mole. So that's how you do these problems. You have to use what you have and work your way to what you want, and you have to use logic. Okay, you have to use logic, you have to use your equations properly. Next problem, question 11. Hopefully you guys tried it. So again, we're going to start with our formula. In this case, it says calculate the freezing point. So what that means is that we're going to use delta TF equals KF times M. And we have to ask ourselves, what are we looking for? We're looking for the freezing point of a solution. So again, if we're talking about benzene, whatever the freezing point of benzene is, that will drop. Okay, that will drop because we're adding a solute into it. We're adding carbon tetrachloride into our benzene. So it's going to cause a depression in the freezing point. It's going to cause a drop. So we're trying to find delta T because that's what the question is asking for. It's asking for some sort of temperature change, and from that we'll subtract the freezing point of benzene minus this answer to figure out the freezing point of the solution. So Kf is for benzene. So K is for the solvent. So we're going to use 5.12 degrees Celsius per M. And the molality of our solution, which is moles of solute, which is carbon tetrachloride, it's the one that has the lower mass. And we're going to convert that to moles. So I'm going to plug it into the equation right away. And the molar mass of carbon tetrachloride, 1 carbon, 4 chlorines, it's going to be 153.8 grams per mole. So that will give us moles, and if you divide that by the weight of the solvent in kilograms, you're going to get this, right? So that's moles per kilogram, and when you solve, you're going to get a temperature change, and it's going to be 4.66. So what that means is that the temperature is going to drop by that much. So if you look at the freezing point of benzene, it is 5.5 degrees Celsius. So that's pure solvent. We throw in carbon tetrachloride, it's going to drop, okay, because that's what happens when you add solvent. And so the freezing point of our solution is going to be 0.84 degrees Celsius. Okay, if this asks for boiling point, it's the same equation, it's just related to boiling. So delta TB equals KB times M. If the problem's ever asking for mass or molar mass, you're gonna solve for M. Okay, if it's ever asking for some sort of temperature, then you don't have to solve for M. You're gonna just plug and chug. Plug it in, find your answer, and adjust as needed. All right, so there's that one. And then the next question is question 14. So real quick, pen here. So it says a 4 molar solution needs to be diluted to make 100 milliliters of 2.5 M solution. So what that's saying is that you have a stock solution of 4, right? And you don't know how much you're gonna need of that to make 100 mils of a diluted solution. Use M1 V1 equals M2 V2, and M1 is going to represent our stock solution, our concentrated solution. We don't know how much of this we need. We want to dilute it to 2.5, and we want it to have 100 mils at the end. So it says how much will be needed to dilute to make that. So that's what we want to end up with. So we're going to put that. And when you solve for V, you're going to get 62.5 milliliters. So that's how much stock is needed, right? And then you're going to add water until it reaches the 100 milliliter mark, and that's how you make your solution, right? Related to the lab we did. Part B is a little different. It says how much deionized water will be needed. We needed 62.5 mils of stock, right? That's our previous answer. That's how much we needed, okay? But the question is saying how much water was added, right? How much was added? And so that's what I was saying, that if you subtract your total by how much stock you used or you needed, that's how much water you're going to need, which is 37.5 milliliters. Okay, so that's how you solve number